and see if I can get my whiteboard up. So far, so good. And where was I? Can I find the last one I was using? That looks like it. Can you see the whiteboard?
Yes, we can see the whiteboard.
And can you hear me? Obviously, yes, you just replied. Right, guys, let's see where we were. Last lecture, I was dealing with image equalization. And the aim of image equalization was to get the best image. That means enhancing the detail in the white area and enhancing the detail in the dark area. And the strategy was to take a histogram, and the histogram would be something like that. I'll draw it as an analog graph, but in fact it is a series of entries at integer intensities. And this is the number of pixels at that intensity. And the simplest image equalization is 2-band. You can do it in 3, 4, 5, 6 bands if you wish, but nothing as complicated as that will appear in the exams, if indeed this is a question. And the idea of equalization is you find your G min, you find your G max, and make a judgment to take into account any faults on the CCD, which will give automatic G min at 0 and automatic G max at white. So those are subjective decisions. This is the area you're interested in for the image. And for 2-band equalization, you find the G 50%. So this is going to be band A, and this is going to be band B. And each of those bands will contain 50% of the pixels. And equalization in its simplest form, whoops, what are we doing there? I've gone to haven't got to the end of there. Oh, well, that'll be a mess, but never mind. I think that's, yes, that's the end. Started at the wrong place, sorry about that. Right. There is G min, and there is G max. You find G 50%. And for 2 bands, that will give you 2 bands of the histogram, A and B, each contain 50% of the pixels. And step 1 is to take band A, and we want to spread this between 0. Oh, don't you start zooming. Band A, we want to change from G min to 50%. G 50% becomes 0 to W over 2. So we would shift the bottom band G min to 0. Forget about the band B at the moment. G min to 0 with an intensity shift. That would take G 50% to G 50% minus G min. You then expand so that the band goes to W over 2, which will be an intensity multiply, and the multiplication factor will be W over 2 divided by G 50% minus G min. And that will shift Gmin to G50% to 0 to W over 2. That's straightforward. That's really just normalization over half the histogram. For band B, the first thing to do is shift to 0. And so your K will be minus G50%. And you have to do that because if you don't shift band B to 0, when you multiply, this will go out of scale if the bottom isn't at 0. 0 is anchored at 0 when you multiply, and it doesn't move. So you shift to 0, you then normalize between 0 and W over 2. So we've now got band B sitting at the bottom, and then you do a shift for where K will be equal to W over 2, and that takes band B to W over 2 to W. And that will give you an equalized image. Both bands will contain the same range of intensities, and that will give you the best quality image. And of course, having done that, don't forget you need the pixel update table. And you then get the enhanced image. So don't confuse equalization and normalization. Normalization is the simple operation applied across the whole histogram. Equalization is local normalization in bands. Okay, now that was a slight diversion because I should have had that before I was talking about window operators. That was last week's lecture. Now this week, I want to talk about double window operations. And this is essentially edge detection. Edge detection in image, extremely important. We want to determine boundaries between regions. It's used for image segmentation. Sketches, you draw a picture, you will be using edges, which represents a complex image. If you look in the room you're in, edges, the corners of the rooms, the corners between the ceiling and the walls, those are edges, and they can be quite difficult to detect by computer algorithms, but they are easy to see by humans. So humans can do the job, computers do it less well. And clearly, when we're moving to autonomous vehicles, yes, they're working pretty well on motorways. They will sort of drive themselves with the lines along the side of the road. But if you really want a completely autonomous vehicle, drive down a country lane. You're going to get a very strange edge between the grass and the edge of the road. And we as humans cope with that quite easily. With edge detection, that's quite a challenge. So let's have a look at traditional edge detection. In the old days, when you had an analog image system, if I take an image that looks like this, and let's supposing this is black, and the other half is white. When we were using the old cathode ray tubes, we would scan the image starting from the top left-hand corner, and we would get a video waveform, which was a voltage against time. And for the black region, it would be something like that. And going across the image, we would get an edge, which would be like that, and we would be then at a higher voltage. This corresponds to the black, and this region would be the white. And to detect the edge on that signal, we can differentiate. Differentiate the video. So if I've got my graph there, if I want dv by dt against time, and remember that differentiation, I'm sure you know, is the slope. We don't need to know the equation to do the differentiation, just look at the slope. And the slope will be 0 up until this point. Drop a line down there. The slope will be 0. The edges don't change instantaneously, so looking at the slope here, the slope will go from 0. It will start to increase as we go round that bend. And so it will start to go up. It reaches a maximum value at this point, and then it starts to ease off. And we are back. Whoops, got it wrong. Halfway down, it starts to ease off. The slope is getting less. Oh, stop it. And it starts to reduce, and it goes down to 0. So going through there, 0 slope, maximum slope in the middle, and down to 0. And of course, that will correspond to the edge between the black and the white parts of the image. Now, thinking back of image processing 20, 30 years ago, that was okay for vertical edges. Because the scan on an old-fashioned TV was horizontal, and differentiating that will give a horizontal scan across there, will give the vertical edge. To get the horizontal edges, we need a vertical scan. And this wasn't readily available. I suppose one choice was to rotate the camera. By 90 degrees. But that gave rise to all sorts of alignment problems, and it was messy. Let's call it messy. However, when we come to digital images, life is a lot easier because we can take a pixel Aij, which is an array in your computer after it's come through the CCD array, and you can scan that vertically and horizontally. In fact, you could scan it in any direction by having an algorithm which changes the I and J. So vertical scan and horizontal scan easy. So life is getting easy with digits. And the first digital edge detector I want to look at is a very simple one. It is the Roberts edge detector, presumably named after a guy called Roberts. Haven't come across him, but that's a good guess. And the Roberts edge detector is an operator that operates on all the pixels A, I, J in an image, and it has weights before and after the pixel you're operating on, A, I, J, and the weights are -1 and +1. Now, that is the normal way of displaying the operator, but I prefer to use a window. Doesn't make any difference, but it ties in with the previous high-pass, low-pass filters. I prefer a window. If you answer an exam question and you've been reading my notes, you'll give me a window and you'll get full marks if it's correct. If you're just taking it off the web and you use just the 2-pixel operator, you'll still get full marks, but there we are. And so the window operator for the Roberts, there is your A, I, J in the middle. all the weights are 0, except the one before and the one after, which are -1 and +1. And of course, what this is going to do, it's going to measure the slope of the image as the window scans part of an image. Now, let's take an example of part of an image. And I'll do a 6x3 picture as an example. There's 6x3. And the intensity is, assuming it's 4 bits per pixel, grey image. Let's have a black region there. And we have a white region, 15, 15, 15, 15, 15, 15 on the right-hand side. Now, if I take my window and scan the window across the image, so this is going to be my window. There's the first position. That is going to produce an output pixel. It will only be looking at these two cells, the minus and the plus. Of course, it's all 0, so the output would be 0. So the pixel there would be 0. Move the window one step, 1 pixel to the right, and we will have +15 minus 0. We will have a value of 15. Move the window again. We will have a value of 15. Move the window to the right-hand side, and we will have 15 minus 15, 0. We get an output when we transverse the black-white edge. And so this is the edge. But it is the vertical edge. And that was easy with old-fashioned analog electronics. What about the horizontal edge? We use a second window, and the weights in the second window are going to be, I'll use my 3x3. It is going to be 0, 0, 0, 0, 0, 0, 0 in the middle, but the key ones are +1 and -1. And again, it's easy to access the pixels above and below simply by changing the coordinates of the pixel ij. So there's no problem there. And that gives us a, if you correlate that with an image, let's call this image EV. Come back to, don't you disappear. And that will give you EH, which is the horizontal edge strength, because it's measuring the intensity above and below the pixel you're operating on, and that will detect an edge if the image is like that. So we've now got 2 edge components. Next step, combine EV and EH to get total edge strength. And there's 2 ways of combining. They both have the same effect. E, the total edge strength, is equal to the square root of EV squared plus EH squared for every pixel. That is essentially Pythagoras, or a simpler way of doing it. Come on, don't play up, whiteboard. We can have E is equal to the mod of EV plus the mod of EH. And you've seen that sort of notation before in the approximate distances, so it's not a new concept, combining moduli to get the overall effect. Right, having done that, the resulting E is a picture, a series of intensities at each pixel location. And let's take an example. Supposing, having correlated the EV operator with the image and the EH, combine them to get the overall strength. Supposing we get an example of E, and let's give you a 4x4. Supposing that example is 0, 5, 12, 15, 4, 15, 12, 7, 15, 4, 14, 2, 4, and 12, 2, 1, 1. So that might be the result of the two operations. Where's the edges? It's just a picture. So the next step is to apply a threshold. And this can be problematic. How do you choose the threshold? Well, really, trial and error. Having got your edge strength, change the threshold, physically look at it and see which is giving the best edge quality. And looking at that image, if I think there is a if there's an edge there, apply a threshold. Let's apply a threshold T equals 10, which means if it's below 10, it's not an edge. If it's above 10, it is. And if I did that to that image, again, we will get a 4x4 image. And below, going through the pixels, the top row, below 10, no, yes, yes, above. If it's above the threshold, it's 1. If it's below, it's 0. Second row, 0, 1, 1, 0, 1, 1, 0, 0, and 1, 0, 0, 0. So looking at that, we've got some 1s in the middle and some 0s on the background. Now the output, 1 is usually black. When you draw a sketch, you draw black lines on white paper. 0 is white background. So looking at that image, if I now convert it to an image, it is going to look something like that. Let's have a black pen. We're going to get a bar in the middle there. Those are the regions. That's going to be black. And there is your black line. There is your edge. Now going back to the original image. Oh, no, that was an example I chose. So we don't know what the original was. So that is the final output. And you have to use a little bit of assessment and exploration, interaction to get the best edges from images. Okay, so that was the simplest edge detector. And it has a slight problem because, well, a big problem. If I go back to the operators, these operators, the horizontal window and the vertical window, they will miss diagonal information. If I put a diagonal line in there, the vertical and the horizontal operators would miss it. So it clearly is insensitive to diagonals. And an improvement to the Roberts is the Pruitt window, presumably named after a Mr. Pruitt, or doctor or professor maybe. And I will just give you the operators because the principle is the same as the Roberts, and the windows, the double windows for the Pruitt. EV, the vertical detector. I'll use my 3x3 window again. Don't you move. Is going to be -1, -1, -1, +1, +1, +1, and the rest are going to be noughts. And it's operating about the central pixel as usual. So we're not only taking the difference between the adjacent neighbors to the center pixel, we're also taking into account the diagonals, and that gives it slightly more effectiveness. That would be EV, and EH will be +1, +1, +1, -1, -1, -1, and naught in the middle. Correlate those two with the image, combine the edge strength threshold, and you will hopefully get an edge image. Now, the criticism with the Pruitt although on a pixel image, all the outer squares are neighbors to the center, in real life, the physical distance is not the same. And we've got this 40% error coming in on neighbors of a pixel. The vertical and the horizontal are unit one away, but the diagonals are further away in real life. They will be root 2. So the Pruitt weights for the diagonals the same as the vertical and the horizontal neighbors, and we can improve on that. In fact, it has already been done. This leads us to the Sobel window detector, edge detector, which is an improvement on the Pruitt. And the two windows for the Sobel EV -1, -2, -1, putting more weight on the horizontal left-hand neighbor than the diagonals. 0, 0, 0, +1, +2, +1. And that will detect the vertical strength, and the second window will detect the horizontal strength. And this will be +1, +2, +1, +1, +2, +1. Now, why 1 and 2? Well, the true difference in distance is if the horizontal left-hand pixel is a distance of 1, the distance of the diagonal is root 2, and that is 1.4. Now, we don't want floating point numbers on the processing. Integer numbers takes enough time for large image processing, so we don't want to go down the route of weights of 1.4, especially in exam questions, which would make the arithmetic tedious. The closest we can get is 2 and 1. If I set them both to 1, we would be back to the Pruitt operator. So those are the weights. Now, an example. Of using the Sobel. And this is a sort of question that might have appeared in exam papers in the past. So just to give you a clue of what might be asked. No guarantees, but this is a typical question. And I will take off example. Oh, come, don't you disappear. How are we doing for time? Yes, we've got 20 minutes left. That should be just enough. Right, let's take an image. And I've got to go to 5 by 5 for it to be meaningful. Remember, these would be on 4,000 by 4,000 pixel images in real life. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And the image I want to use, 4 bits per pixel. In real life, it would be at least 8 bits per pixel. Color would be even more. And the intensities don't you disappear? The intensities I want are 0, 0, 0, 0, 15. 0, 0, 0, 15, 15. 0, 0, 15, 15, 15. 0, 15, 15, 15, 15, and all 15s at the bottom. And clearly, if you had that image in front of you before digitization, the image would look something like this. It would be a black region there. And a white region beneath it. And we want to detect the edge between the two. Right.
John, you've put a 0 on the bottom right.
I have. How silly of me. It could happen, but it will just make the math slightly more tricky. So let's keep that one black. Keep the other one white rather than black. Yeah, that was a pixel that was dud. It went to 0, but it should be 15. Right. EV. The vertical window is -1, -2, -1, 0, 0, 0, +1, +2, +1. And that window has got to sit initially over that part of the image. And doing the correlation, we can see, let's keep the whole thing in view. Ah, don't! You bugger. EV, of course, will be a 3 by 3 because we will lose the edge information the same as we do with high pass and low pass filtering. Devastating at low resolution, irrelevant at high resolution. So the only non-zero output is going to be 15 times 1. That cell is going to be 15. Move the window to the center of the top. It is going to be 15 by 230, 45 minus 0. It's going to be 45. Is that right? No, it's wrong. It's wrong. What should it be? Naught. 15 times 2 is 30. Plus 15, 45. And there's nothing on the underneath the negative weight. So it's going to be 45. And the next position is going to be 15, 30, 45, 60, minus 15, 45 again.
John,
Right, moving down to the middle, shift the
John.
window down. It's now going to be there. And that is going to be 30, 45, naught minus is going to be 45. Right in the center, it's going to be 60 minus 15. That's going to be 45. And on the far right of the center, it's going to be 30, 45, 60 minus 30, 45 is going to be 15. And now the bottom row, 60 minus 15, 45. In the middle, it's going to be 60 minus 45 is going to be 15. And at the bottom, it's going to be 0. And that is EV. Now correlate it with EH. And EH is going to be +1, +2, +1, -1, -2, -1. And if we do that correlation, when I did it earlier this morning, I came out with these results. Well, let's do the first one. The first one is going to be sitting in the top left. It's going to be 0 on the pluses. It's going to be -15. Yes, you can get negative values. That's quite possible. And I think the other values are -30, -15, -45, -45, -15, -45, -15, and 0. And that is your EH strength. Okay. We now need to combine them. And we have E, the total. We can either use Pythagoras, or usually it's in exams, follow the rule, keep it simple if possible. The simpler one is the sum of moduli, EV plus EH. And that is going to give me my E picture, adding the modulus of those strength maps, EV and EH, is going to be 15, and mod of -15, of course, is 15. It's going to be 30. It's not 0 because you're adding the mods. The next one is going to be 75. The next one is going to be 60, 90, 90 and 15, and at the bottom 90, 30 and 0. So that is E.
Is the last column in the middle 30, not 15?
15, 30, thank you very much. Yes. 30. There's your edge strength map. We still haven't got the edge. Now the threshold comes into play. And it is subjective. So if you're actually trying to optimize this in real time on a real image, you would scan a number of thresholds, look at it as a human and make a judgment as to which is the best. But in this case, we've got to be make a stab at it. And what I'm going to suggest is a threshold. Try t equals 50. And looking at that, right, below 50 it's 0, and above 50 it's going to be 1. We're going to get 1, 1, 1, 1, 0, 1, 0, 0. So there we are. There is the edged image. Of course, that is going to be the black region because 1 will be black and our image edged will look like that. A single pixel, a single line, which should correspond to the edge there. So it has detected the edge. Getting the threshold right can be tricky. If I said, let's try another threshold. Try t equals 80. Now, what sort of image does that give us? Keep the other one in view. If I dare reduce it without losing my picture. And that is going to be naught, 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 1, 1, naught, 1, naught, naught. Okay, it's not going to give the whole continuity of line. That's less good. Okay, now the weights. You're in an exam, you're using the Sobel operator, you're using the vertical detector, EV. You remember that the weights are 1, 2, 1, 1, 2, 1. You can't remember whether the left-hand side is negative and the right-hand side is positive or the other way round. The sign doesn't matter. As long as same sign in the column, i.e. we can have all those negative and all those positive, or all those positive and all those negative. It will still detect the edges because we are either using the square or the modulus when we combine them. Well, there we use the modulus. The sign doesn't matter. So we will bring out the edge strength, but what you can't do is mix the pluses and the minuses there. So this would equally be a valid edge detector. And a further thing that one can detect from the edge detection is the direction of the edge. And if you want to get the direction of the edge theta at any pixel location, theta equals tan to the -1 of EV over EH. And depending on whether the sign is positive or negative, this will determine what the zero angle is. In one case, the zero angle will be there, or the angle from that point. In the other case, it will be an angle from that point. And you can calibrate the edge detector depending on what you've chosen. So it still works even if the coordinates, the polarity is reversed. That applies to the Sobel, the Pruitt, and the Roberts, which is the early one. Okay, how are we doing for time? I've only got a few minutes left. So other edge detectors. I just want to mention the Canny. It's a better edge detector, but it is considerably more complicated, and I won't be asking questions on the Canny in the exam. But basically, the Canny is a much larger window. Perhaps 16 by 16 pixels in the window. And the window is a Gaussian. I.e. the weights horizontally will be a distribution like that, and the weights vertically will be the same. So we get a sort of Mexican hat type of window. And that correlates the image, and you track the maximum output. And no need for threshold. That's a great advantage. So you've heard of the Canny now. If you're in a job interview for image processing and somebody says Canny, at least you're familiar with it. Right. I've said edge detection is difficult. It is. Intensity changes, which all these methods are relying on, does not necessarily define an edge. A problem. We're using intensity and it's not reliable. And to give an example, a common example, if I were to draw a face, which is a form of edge detection, I would put the ears, I would put the eyes in, I would put the mouth in, I would put the nose in. Very important. A face without a nose looks rather strange. So we would always sketch in a nose, maybe a little bit more detail on the nose. There we are. Very interesting. Now those edges which define the nose don't exist as intensity changes. So there's more to an edge than a change of intensity, and this involves an understanding of the nature of the data. And again, looking at the room you're in at the moment, look at a corner of the room between two walls. The paint most probably is exactly the same color. It's a 3D change, but if you were drawing that room, that edge, there's a wall there, there's a, I don't know, another wall coming out. How can I draw it? Looking like there's an edge down there. Now that could be the same paint, that could be the same paint. There's no intensity change as we go through that area, but we would assume it is an edge, and it's an important structural edge. So very briefly, how's time going? I've got 2 minutes left. Another idea. If we don't know what to measure, but we know there's information in the data, neural networks, let them learn the edge. And to give an example of a pattern which might require, well, it certainly wouldn't work with Sobel, but might require a new type of edge detect. Supposing I took a shaded area, chevrons like that. And so that is one form of data. And the other form of data, what's happened? Go away. And the other form of data, if you applied a Sobel or a Roberts or a Pruitt to that one, because they are edgy and the main body of the texture is made up of edges, it would bring out the stripes. The real edge on that particular image is down there. And the 3 edge detectors I've talked about this morning would fail on that. But if we took a neural network, extracting patterns, take a window in the edge area and train on images on edge, then maybe we could get an edge detector to detect that artificial edge. Okay, it's pretty artificial, pretty fictional, if you like. But supposing you've got a image with a track going down a road. There's sort of, and you've got grass growing along the side here. I've got some pictures in my office of this, but unfortunately I haven't got them with you. Supposing this was a track and this was grass, then clearly this boundary there is a crucial boundary, edge of road. Okay, it's a country lane, but you can walk along there. If this was a river and this was the footpath, you keep safe. You recognize that boundary. And boundaries, edges like that in real world, which we take for granted and we recognize, are extremely difficult to detect using algorithms. So there's still plenty of work to do on edge detection. It sounds a simple thing to do, but when you try and implement it in computers, it is tough. As far as exams are concerned, concentrate on the principle of edge detection, the Roberts, the Pruitt, and the best of those 3 window type ones is the Sobel. Okay, that's all for today, guys, and I'll see you next week. Any questions? Right. Turn off